Hey, hi everyone, this is Vivek and welcome to yet another episode of Atcoder Weekly. Today we're going to talk about this particular problem, foreign friends, which is a very beautiful problem on graph. Essentially, how do you tweak shortest path algorithms? Now, this is about this concept called MSSP or multi-source shortest path idea, which I think is common for creating questions. But if you have not seen some question on top of that, I think this is something that is going to be a very important learning. Also, this problem has two very important learnings, so make sure that you watch through the whole video to learn the both of them. Also, for this particular channel, I was in a bit of pause right for like last 3 weeks for some other work, and then I was also traveling, so due to that I could not create videos, but I'm back, and then the videos are going to flow continuously from this point going forward. And I'm going to also add this one more section, which is people's choice, where you can suggest me which problem to take and explain, because I think a lot of people suggest me that, hey Vivek, you can take this question, but there is not a structured way to take that. So what I'll do is I will kind of you can go down below in the comments and add the link to the problem that you want me to explain, and I'm going to choose the one that has good amount of learning, and people vote as well. So do like the problems that you feel are interesting. There are two things for this. Number one, we will have some good problems to practice for people who are watching these videos. Also, like some problems that I might miss on because I'm not really actively giving all context, but has interesting ideas to be covered, can be surfaced out in these comments, and then I will take up in that particular section. So now from now on there will be 4 videos every week, the Atcoder, leetcode, and codeforces, and alongside that we will have that people's suggestion problem. Okay, so make sure that you comment down for any problem that you think that I should make a video on, or something that you felt like, okay, this should have a good video editorial, and you have been confused about the concept for a long time. So make sure that you add to the comment. Let's come back to this problem, because let's not deviate from the main agenda. So this foreign friends is a problem which is a very interesting idea on graphs. So they're given 1 to n persons, 1 to k nations. You're given that which person belong to which nations. Among the persons there are some leaders or popular persons, and among them you can also make m of them as friends. So if you read the problem, it's essentially given that you can make two person friends. So it's like there is this person's graph that is given to you, and there is edges between them. If you need to activate them, you will get a cost of c of I, right? And there are nations tagged with every person, and some of the persons are like popular. Now what we need to do in this particular problem is, for every person, essentially you have to find one of the popular persons from some other nation altogether. So if you have a particular person I, and then you want to find some other person J, which is not number one in the nation of I, and number two is a popular person. So can we do that? Yes or no? So this is something that we need to solve in this particular problem for all I's. That's the beauty of this particular problem. How can we do that? So solving for a particular I seems to be simple. Like you can simply run a shortest path algorithm. Like since it's a weighted graph, the costs are ci, you can run a Dijkstra from a node, and then you can get the distance to every other node, and then you can loop over for all the other persons and check if it's of a different nation and is a leader, is a popular person, then you can kind of update that. But in this problem you have to do it for every node, which is the main tweak in this question. So how do we solve something like this? Let's move into the drawing board and understand how to solve this. So the setup that we are given to us is something like this. This is just a demo graph, and we have these nodes as the persons, 1 2 3 4 up till 8 persons are there. And a person, like if something is shaded, it's like a popular person, and then the color or the namings B, C, D, A, these denote the nation type. Okay, and the numbers denote the persons. Also in the question we are given a weighted graph wherein the connections have some weights, but for generality I'm just removed it, and we are like processing in a simpler manner. The general version with the weights can be processed very simply by changing the algorithm. Like what algorithm do you use instead of for weighted and unweighted is what changes, except that everything else remains same. So I'm just removing out the weights for now and processing it as if it's an unweighted graph. So now we have given that we have to find for every node what is the shortest path to one of the shaded nodes which is not in the same nation. So there are two constraints to it, right? So how do we solve these problems? How do we go about thinking about this, right? So the first thing that clicks my mind is, number one, that I have to think about, for every node I need to find distance to the popular nodes, right? For every node I need to know distance to the popular nodes. The second condition is its nation should not be of the same time. But forget about the second constraint for now. Let's say everybody is of different nation from a given node, right? We don't really care about the nation constraint. So for every node, you have to find the distance to one of the popular nodes, the closest popular node. How to do that? That is a very interesting problem in itself, and what is called as MSSP problem. Let's go about understanding that. So the question is, for every node, find out the closest popular node. Okay, be it weighted or unweighted, the only algorithm changes, but the concept remains the same. How to do that? So the way we do that is, like, let's say if you're given like this, the way we think about this is, we just, like, if you had to find out the shortest, like, let's say this was the only popular node, and then you had to find for every node what is the closest popular node, you would run a BFS from this particular node or a Dijkstra from this particular node when it's weighted, and find the distance to every other node, and then you know the answer for every node, right? But now you have multiple popular nodes, and you need to find for every node the closest one out of that. So the way we can do that is, in the BFS, if you remember, the code goes something like this, that you push this particular node 8 in the BFS and then mark its distance as 0 and then start the BFS, right? This is how we write BFS. The way to change this is, you add all the nodes that are at a distance that are popular, 1 at a distance 0, and then from this particular queue instance you start the BFS, right? And then whatever distances you get, you will see that 8 will mark this as 1, then 8 will get removed, and then 7 will get inserted in the queue. Then 4 will mark 4 will come out, 4 will mark this at distance 1 and this at distance 1, then 3 and 5 will be inserted, right? And 4 will be removed, then 1 will get removed and 2 is marked at distance 1, and then 2 is inserted, and then you can see that everything, like, when 7 gets removed and then 6 is inserted, 6 is at distance 2, and you can see that every node now has a distance. 4 is at 0, 0, 0, these are at 1, 1, 1, and this is at 2 distance, right? This is at 1 distance as well. So everything kind of gets its own distances if you do it this way, and this is the main idea that we use for this particular type. The reason why this works, this is a very interesting idea. Why does this idea work when we put everything in the queue? So the reason this works is, let's say if you think about, let's say, a super node, right? This is the concept of super node, which is connected to every other popular node using a single edge, right? And now we run a BFS from this super node. We put in this super node and then we run a BFS. So the super node will have a distance 0, and then we see that all of these first popular nodes will have a distance 1, 1, 1. And then now you think about any particular node's shortest path to the super node. Okay, so the way it will work, is it will go to one of the popular nodes and then it will take an edge to go to the super node, right? So every shortest path from this super node to any node is like connecting the other node that we're connecting to the super node to the closest popular node, and then using one more edge to go to the super node, right? So that is the exact same process that we are doing, except that we are not putting this S first. Instead, we are removing the first step of the BFS, where we take out the S and then insert all the neighbors into it and then mark the distances as 0. We will directly start with the 1, 8, 4 and 8 in the queue and then mark their distances as 0. So this is the way in which single source shortest path idea works, wherein for all the sources that are there, right? So let's say there is bunch of x1, x2, x3, right? And there are bunch of nodes y1, y2, y3, right? There are a bunch of nodes, and for each y1, y2, y3, you want to find the closest node from this particular set. Okay, so the way we work with this is, put all of these nodes into the queue at a distance 0 and then start a BFS. Then whatever distances you get for every node, okay, you will get the distance to closest x, from y. That is the distance that you will get. Okay, so this is the first idea, which is called MSSP, or multi-source shortest path. For every node, find the closest source node out of the set of nodes. So this is the first thing that is used in this particular problem, that out of these popular nodes that are given in the problem, we need to find the closest node. And in this problem, it is given weighted. So what we'll do is, we will use Dijkstra instead of this. So I said that this is a BFS and we are putting these nodes in the queue. Similarly, just replace this queue with a priority queue and you will get the same idea. So in BFS, in 0, 1 BFS, in priority queue kind of data structures, like in Dijkstra, all of these three variations can solve problems where you have multiple source and you want to find the closest node, the closest source node from any node, right? If that is the problem that you're solving, you can use this particular idea. Now in this problem, we have again a second constraint into things. So this is the first learning, right? MSSP idea. Now in this problem is like one step ahead of this. The question says that we also need to like take into consideration this nation type, wherein like for a particular node that is given to us, we need to find the leader node, but it should not be of the same nation, right? So for this particular node, if you think about it, the closest popular node is this, but they are the same nation. So essentially you need to consider something else, and the closest one after this 8 is 4, which is of different type. So the distance for the number for this would be 2, right? So now we don't just need to find the closest popular node, we need to find the closest popular with different nation type. So how do we process this second constraint, right? And this is again a second tweaking of Dijkstra. So the first tweaking was, how do you handle multiple sources? How do you handle finding out something of not of the same type as itself, okay? And this is something that is generally used in other problems as well, and there is a very generic type to this. So whenever we need to find the closest popular node, we need to first understand that if we keep the closest two nations, okay, if we find for every node what is the shortest path to two different nations popular nodes, okay, if we find the closest two distinct nations popular nodes, then we are done with it, right? Because out of the two shortest ones, if the minimum one is of the same nation type, then we will take the second one, or else we will take the minimum one. So if we know the two minimum different nations popular nodes, then we are done with the problem, right? So this is the essential idea that we're going to use for this particular problem, that for like in the first setting that we had, there was these nodes from which we had to calculate the shortest path to any one of them, right? Now for every one of them, we will calculate shortest path to two of them, two different types, like there are types to this, T1, T2. So we will find out two different types, find two closest shortest paths, one of type 1, one of type 2, such that type 1 is not equal to type 2. We need to do this, okay? How to do this? This is the main essential idea for this problem. So the reason why we cannot do it something other way is like, you can try out more other ways, it will not work, okay? Like handling the nation first is not something we can do, and like there is more ideas that you can think about, is maybe processing each nations individually and then connecting them somehow, but those ideas also don't work. Like I thought about those ideas initially, but that didn't work. The more clear idea is like modifying this MSSP to handle two different types. How to do that? So let's look into that. So essentially when we start from this, we know that, so what we'll do is, for every node, okay, every node X, we will find two different distance array, D1 and D2, okay? D1 is the closest popular and its type, okay? So D1 for every node X, D1 of X will store two values, the distance, the closest distance to popular node, and its type of the nation of the closest one. D2 of X will store closest distance to popular node whose nation type is not equal to this nation type, okay? There are two different distances that we will compute for every node, okay? How we will handle this in Dijkstra is the most beautiful stuff in this particular problem. So if you remember the Dijkstra's code, when we take things out of priority queue, right, we mark them as visited, or we mark them as done, that this node is now set with its smallest value, and then update the rest of the things, relax the rest of the nodes, relax the edges from it. In this particular thing, we will wait for a node to be taken out from the priority queue twice with two different nations, okay? We will wait for the second time to occur. That's the beauty of it. So when we will put things, so earlier we put the distance comma the node in the priority queue, now we'll put distance, the node, and its type, okay, the type from which this particular shortest distance is being generated, okay, type 1. So let's say the first time a particular node is taken out from the priority queue with the shortest distance, so we will mark its D1 of that particular node as D, okay, and we will mark the current value, okay, of n as T. Now again, let's say the next node that gets is something like d2, d some dx, and then n again, and then t1 again. So let's say you get another, so from some other way, so for some other same type of nation, you get another shortest path dy, right? So in that case, you will see that the d1 currently already has the distance d with the same nation type. So this is obviously worse than this because this has been taken out of priority queue later on. So don't process this one. Sometime later from the priority queue, you will get d some dy, maybe something else, and then n, and then some nation type t2. So what you will do is you will do d2 this time. We will process this because this is not of the same type as the previous one. So the shortest nation is t1, the second shortest nation is t2, okay, and the distance to that is dy, and the second one you don't even need to store, because if the first one is not of the if is of the same type, then you use the second distance, or else you use the first distance. So you don't even need to save the second type, but if you want you can. So this is the whole idea, that you let every node relax twice. Once when it's of the when the shortest path to from any of the popular nodes is coming out, okay, that's the first time. The second time is next time, every time you get the same nation type, you just discard them off. But the next time you get another particular node at another particular tuple at the same node with a different nation, you save that distance as well and then relax again. So you allow it twice instead of once in the Dijkstra. That's the main idea of this particular problem. I will go ahead and explain the code for this particular thing, because just explaining it directly using this might not make it 100% clear. So I will use the editorial code directly, because that will make it more clear. Let's go ahead and understand from that. So let's go to that, right? So you can see that when we see a particular node x, which is a leader, we put 0 distance, okay, at the leader x, like the node number is going to be x minus 1, right? This is caved in a 0 indexed way, and the nation type of 0 minus 1 is taken over here. So 0 distance at this node with a nation type of a of this, right? These are the nation types taken earlier. Now we take these edges, these are the cost edges, and then we like simply do the Dijkstra. This is the standard way to do Dijkstra, and the way we do this is we put distances in negative direction, and then this is just a standard Dijkstra. I mean, I don't need to explain the code of Dijkstra. I think you guys are very much aware about Dijkstra if you're watching this video till this point. So what we have is this used, which is like a marker visited array that we keep in Dijkstra, and it's initially 0. Now when we see the first time, it's actually equal to 0, right? When it's if it's equal to 0 and it's not equal to y. So first time it's 0, and none of the nations is like, the nation numbers are 1 2 3 4 up till k, so it's not 0. So the first time you get it, if it is 0, then we will mark its distance as minus z. We are keeping the negative of the, so these z values will be negative, because in priority queue you know that it sorts from lowest to highest. The highest one comes out, so you have to negate the value of the distance. So the negative of the distance is stored at distance. The current used, like the city that is kind of giving you the minimum at this x is y, right? And then you mark that this node has been touched once, so 0 to the city that has been marked, that has marked it once, so you have that as y, okay? So next time a second tuple comes with the same node, right, it will see that it is greater than equal to 0 because it's y, and if it's equal to y, then it will not process it. It will just discard that off, and it will not relax, right? The main constraint, main time complexity comes in Dijkstra from the relaxation of all the edges from that node. If you're just popping out things from the queue, that's just the number of times you can insert things in the queue, in the priority queue, and that's generally restricted by the number of edges, number of traversal over edges, right? Because every time you relax an edge, you add something into the priority queue, so you think it that way. And the second time you see something that is not of the same nation type and is currently being, like, it has seen just a single node, single city, so the second distance is what you store over here, and then you mark the used as -1. So note that now it will always false over here. If it's -1, this condition fails and it will always be stopped. So you got one nation type, second nation type, and out of that you save everything. Like, this is just a standard relaxation of edges in the Dijkstra. And then for every node we can simply see that if, like, you can store the if it's infinite, then you store it as -1, and then if you see that every node, if the nation type is same as the first nation is not same as the first nation type, then the answer is first nation distance, and if it is not the case, then the second nation distance is there, right? And you print the array. So that's the whole idea. So the main thing is this: how did this visited array is being used twice in the positive domain, 0 to the, so the transition is 0 to the first nation type, then to the -1, and the second nation type distance is saved. So that's how this used visited array is being used in this particular code. So in this problem, I've already explained the code, so just go ahead and code this particular thing so that you are finally aware about how to do this multi-source stuff. Number one, that multi-source stuff is just take all the sources and put all of them in the priority queue at the start itself. And the second thing that we need to do in this particular problem is how do we use this used array or visited array to mark the two closest distance from the nations that are given, right? A very beautiful problem in this multi-source domain. And I think if somebody solves this one problem, they have this whole idea on how to get first, second, third distances in Dijkstra, as well as handling multiple sources altogether. So this is like one problem that teaches you everything in Dijkstra as variation. So that's there for this particular problem, and I think more or less for this particular video as well. So I hope you learned a lot of things from this. If you learned, do let me know what you learned in the comments. I think I have already talked about the main two learnings that are there. If you learned something new as well while coding, do let others know. Also, do comment what you want to take me to take as the problem in the next one of the people suggestion video, so that I can like kind of keep and counter. And do like others' problem. If you see that some problem, you just open up, and since you are a competitive programmer, you will open up and you will see that, okay, this is something that can be interesting, so let's say take that up. Also, if you have any suggestions for me, or if you just want me to change the pattern, the way I take things in my channel, I'm free to absolutely open to take any suggestions that you have, so feel free to drop them down in the comments. And that's all. Don't forget to like the video, because these videos do take a lot of effort to create, and subscribe to the channel, because we'd be having more such things if you have not done it yet. I mean, if you have not done it yet and you're watching till this point, so you should definitely subscribe. So that's all. Thanks for joining in till this end, and we'll see you in the next video. Bye.